So before doing this solution, before solving this question, I want all of you to just try this question, and it's little bit tricky, I would say. You just have to get that small idea how to do this thing. I, you can just pause the video and you can read the question. The question is nothing but it is not smooth. If it is smooth, we know the change in the potential energy is mgh, and that's why the that work done will be mgh, we know that. But the thing is, it is not smooth, it is having some coefficient of friction, it is having some friction. So, and also this line that is not straight or not any known curve which we can normally calculate. It is some random curve. We have to calculate that. How can we do that? So one thing you can do is you can take it as a straight line and you can solve, because it is a random curve. It can be a straight line, it can be a circle and anything. If you take a straight line and if you solve, still you will get the answer, but we'll see the proper solution. How can we do? They gave that the mass of the body is m, so it is taken slowly up through the height h, and the baseline is L. They're asking how much work is done to take through that much height. So let's see the solution. And so this length is L and this is h. If you see this line, this is like this. If we take a small part dx, we can take it as dx. So this is dx, and we can take it like these are the dl and dh if we make it a right angle triangle, and we can consider a theta here, right? So I'll show it in a little bit bigger manner. This is dx, this is dh, and this is dl, and this is theta. So the block is right here, and the mg is acting downwards, and this is mg cos theta in normally, and mg sin theta in this side. And also there will be some frictional force that is equal to mu mg cos theta, because normal force is mg cos theta, and there is some force acting in this side. So there will be some change in kinetic energy while taking it up through the distance dx. So we can apply work energy theorem, or you can simply calculate the normal negative work done is equal to the change in potential energy. You can let's just use the work energy theorem. So for this small area, change in kinetic energy is equal to small work done. Let's say F into dx minus, because the dx is in the same direction as force, so let's take it as F dx, and F dx is nothing but small work done we needed, that is small work done dw minus the mg sin theta and mu mg cos theta, both are acting downwards, into the small displacement is dx. So this kinetic energy, we can write it as, this is nothing but dke. Okay, we can write as dke, small kinetic energy. And if we integrate all of them, they told that initial and final kinetic energy is equal to 0, of course. So this part will be equal to 0, and we want this work done, so this will be equal to W, and W equal to integration of mg sin theta plus mu mg cos theta into dx. We can just multiply the dx inside. W equal to integration mg sin theta dx. Sin theta dx is equal to, from this figure we can take dx sin theta is equal to dh and dx cos theta equal to dl plus mu mg dx cos theta. Mg into dx sin theta is nothing but dh plus mu mg dx cos theta is equal to dl. Integrating this from initially the height is 0 to h. Initially the amount of distance it moved in horizontal direction is 0 to L, so it will be mgh plus mu mgl. This is the work done we needed. So yeah, this is the energy, this is the work done by force, that's the energy stored.